Hi everyone, this is Professor Mayunger and you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started. Hello viewers, today I'm going to show SFD and BMD of a simply supported beam under some constrained loads. Initially we'll start from simple examples and later on we'll move into a little bit of complex problems one, right? So first one, let us see the statement of the problem. A simply supported beam AB of span 2.5 meter is carrying 2 point loads as shown in the figure. Draw the shear force and bending moment diagram for the beam using ANSYS mechanical APDL and compare the results. Because already we are having the results from the theoretical calculations, we need to find the results using ANSYS mechanical APDL and that to be compared. And we are considering the beam is a square cross section of breadth equal to 0.01 meter and depth is also 0.01 meter. It is a square cross section and the material is having modulus of elasticity of 2 into 10 to the 11 Newton per meter square and Poisson's ratio is 0.3. Right, we don't require density for this analysis. Okay, so let us start finite element analysis of this one using ANSYS mechanical APDL. Right, first of all we need to create a directory and in that directory we need to save everything. After that we can change the title of this one from file, change title, and we can rename this one as FEA1. Okay, and to see the title you can click on plot to replot. It will be visible at the lower left corner, so FEA1 is visible at the lower left corner. Next to that, we need to select what type of analysis it is. It is a static structural analysis. So we can click from preferences and we can click structural analysis. Okay, done. Now we need to define elemental properties and that will come from preprocessors. So preprocessors, element type, add, edit, delete. We need to add it and we're considering beam 3D finite strain with element type reference number 1. Okay. Now from options we can select the element behavior of this one as cubic form. Okay, let us close it. Now we need to provide material properties. As I told already, it is having modulus of elasticity as 2 into 10 to the 11 Newton per meter square and Poisson's ratio as 0.3. So material models, structural, linear, elastic and isotropic. Isotropic means material property remains same in all directions, right? So we can provide a specific values. Modulus of elasticity is 2 into 10 to the 11 Newton per meter square. So 2E11 and Poisson's ratio is 0.3. Okay, done. Let us close this one. Now we need to provide sections of that one. As I told before, this is having a square cross section of breadth equal to 0.01 meter and depth is also 0.01 meter. So we can provide that one sections, beam cone sections, and breadth will be 0.01 meter and height also it will be 0.01 meter. Okay, done. We have provided cross section. Next to that we need to start modeling. While modeling you can create key points, it will be better one. So we can start key points in active coordinate system. We can remember that model was having total length of 2.5 meter and 2 concentrated loading of 2 kilonewton and 4 kilonewton was applied some specific distance away, right? So first node will be created at origin, so we are not providing the zero values. Default zero value it will take, so apply. First node is created at origin. Next node will be created at a distance of 1 meter. 1, apply. Second node is also created. Now third node will be created at a distance of 1.5 meter. Apply. Third node is also made. Now the fourth node will be created at a distance of 2.5 meter. 2.5, apply. Fourth node is also made. Now we'll do one thing. For orientation of this beam we can create one extra point at any specific location. Let us provide the orientation key point at a distance of x equal to 0 and y equal to -2. You see, these are the key points. We already made it. Now the thing is we need to join these points in the form of a line. So it will be coming from lines, straight line, and let us join key point 1 and key point 2. Next one it will be key point 2 and key point 3, and finally the last one it is key point 3 and key point 4. Join, it is a straight line. Okay, now we need to mesh it, and for meshing we need to first of all we need to select mesh attributes. That means we have provided this one orientation point that to be included as a orientation point, right? That will come from meshing attribute. So mesh attributes, all lines, and we're considering this point also as a orientation key point, so we are selecting that. Okay, now again see here we need to pick the orientation point here itself. Let us select the orientation point 5. Okay, right. Now we can mesh it. For meshing, we can start with size controls, manual size, lines, all lines. Let us consider the numbers of elemental division for each line equal to 10. Okay, done. Now we can mesh it. From here, mesh, lines, pick all. Meshing is done, right? Now we can start applying load, and that will be started from here itself. Load, analysis type, it is a new analysis and it is a static structural analysis. Now define loads. Apply structural displacement on key points, because the first point should be fixed, right? So let us select first one, apply, and it will be having some specific movement. So along x, y, z, it will be restricted to move. By the same time, it will be restricted to rotate along x and y direction. Only rotation along z axis is allowed, excluding that all are restricted. Apply. First boundary condition is applied at the node number 1 or key point number 1, and second one to be applied at the last one. It is a simply supported beam, so let us select the fourth key point. Selected. Okay, now here in this case, excluding ux, all will be restricted, like uy, uz, and rotation x and rotation y, all are restricted, right? Okay, done. It's complete. Now we need to apply our loads, right? And for applying the loads, we can see the lines again, plot lines, because we need to apply load at specific locations, right? We need to apply a load of 2 kilonewton at this location and 4 kilonewton at this location. Two different locations we need to apply point loads, right? So we can apply loads from here itself. Structural force moment on key points. Let us select this key point, apply, and we need to apply a force in the y direction, Fy, and the value is 2 kilonewton. It will be in the downward direction, so it will be minus 2000 Newton. First load is applied. Now the second load is to be applied at this location. Let us select that location. Selected. Okay, and again it will be in the downward direction, so negative 4000 Newton we are applying. Okay, we have applied all the boundary conditions. Now we need to solve it. So solution, solve current LS. If everything is right, it will show solution is done. Okay, it is showing solution is done, so everything is fine. You can see our results from general post processing, right? General post processing. And the thing is, first of all, we need to read the results, right? Read results. Let us read it from last set. Done. Now we need to create the elemental table, and that will come from here. Define table, add table. Now the very important thing is, if you want to have bending moment diagram, you need to define a specific numbers, and the numbers will be for bending moment, it will be SMIS 2 and SMIS 15, and for shear force it will be SMISC 5 and SMISC 18, right? Let us select these numbers. We can write here this one as bending moment, or if you don't want, no issues at all, right? We can write here bending moment also. First of all, we need to see bending moment, so it will be from drop down menu we can select by sequence number, and it will be SMISC 2. For bending moment, the number will be 2 and 15, right? Apply. First one is made. Now second one, again by drop down menu we can select by sequence number, and again SMISC, it will be 15. So bending moment diagram will be represented by these two numbers, 2 and 15, right? Apply. Next one, for shear force diagram, we need to select again by drop down menu we can select by sequence number, and here SMISC, it will be 5. Apply, and again repeat the process by sequence number, and you can select SMISC 18, right? Okay, these are the set of numbers you have selected. For bending moment, we have to select 2 and 15, and for shear force we need to select 5 and 18. Okay, let us close it. Now first of all, we will see our results from list results, and we need to see our reaction solution, right? Let us see reaction solution from here itself. All items, you can see it. You can see here that reaction at Y at node number 1 is 2800 Newton or 2.8 kilonewton, and at node number 42, it is 3200 Newton, 3200 Newton, or 3.2 kilonewton. So these are the results. We can check the results from our theoretical results obtained in the question paper itself. Let us see that. You can see that here itself, reaction at node 1 is 2.8 kilonewton, and at last node it is 3.2 kilonewton. It is exactly same what we got in our listing results. Now we'll see the results from plotting. We need to plot BMD and SFD from ANSYS mechanical APDL. So here also you can check it. At node number 1, reaction is actually 2.8 kilonewton, and at last node it is 3.2 kilonewton, right? Now we'll see results as plotting, right? So plot results, contour plot, line elemental response. As I told before, for bending moment we need to see SMS 2 and 15, right? And we can increase the factor by 2 to see the deformation in a higher scale. Let us change the scale to 2. It will magnify the drawing itself. Let us see it. This is the drawing actually, right? You can see, and it is clearly visible that maximum bending moment is occurring at this node, and it is 3.2 kilonewton meter, and you can see at this location it is actually 2.844 kilonewton meter. Now we can do one thing. We can see the node numbers and see at which node bending moment is what. For that we need to look at nodes, plot controls, numbering, node numbers. Let us make it on. Now you can see different node numbers. Like node number 22, at this location bending moment is maximum. It is 3.2 kilonewton meter, or 3200 kilonewton meter, right? And at this location you can see the numbers of node numbers also. It is 23. At 23 node number, bending moment is actually 2.844 kilonewton meter, and minimum is approximately 0. It is very less. It is 0.66 into 10 to the power minus 9 Newton meter. It is approximately equal to 0, right? Next to that we want to see this shear force diagram, and we can compare these results with our original also. It is exactly same. So we can remember this one is maximum bending moment is 3.2 kilonewton meter, and minimum is 0, and it is occurring at this location, right, at node number 22. Now we want to see shear force diagram. So we need to change the numbers from 2 to it will be 5, and it will be 18. Let us see this one. It is the shear force diagram. We can say maximum shear force is actually 2.8 kilonewton, and minimum is actually 3.2 kilonewton. Here it is minimum and maximum is here, right? And we can see our results from our question paper. We can compare these things. It is exactly same what we saw in our question paper, right? We can see the results from the question paper itself. Let us see the question paper. So from shear force diagram it is clearly evident that the results are exactly same, right? Maximum shear force actually 2.8 kilonewton, and minimum is actually 3.2 kilonewton. It is downwards, right? We can compare the bending moment also. We can see it again by changing the numbers from 2, and it will be 15. Let us see it again. So you can see it from here itself again. Maximum bending moment is actually 3.2 kilonewton meter. Here also you can check it. At this point maximum it is 3.2 kilonewton meter, and at this location here it is, you can see at this location it is 2.844 kilonewton meter. So it is exactly same what we saw in our question paper. So it is validating our results, right? Instead of this one, we will do one thing. We can see our results in the form of listing also. Next to that, we want to see our results in the form of listing. That means we want to see all the data in the form of numbers, right? So you can see list results and element table data, and from here we can select SMIS 2 and 15 that will provide data for bending moment. Okay, you can see these are at different nodes we are having bending moment, and at the last point we can see maximum bending moment is occurring at node number 21 and 20. It is 3.2 kilonewton meter, right? And minimum is occurring at node number 1 and 30. It is minus 0.66 into 10 to the minus 9. It is approximately equal to 0, right? This is the numbers, we can save it, right? We can see other things like displacement along y direction also. Can do what? Nodal solution, degrees of freedom solution. You can see displacement in y direction also. Let us check it. So these are the displacement of different nodes along y. At each node we can see what are the different deflections, right? Maximum displacement is occurring here. It is minus 11.063, right? And the location it is here itself. From listing also you can see at which point it is having maximum displacement. That can be seen from listing results also. Let us view that from listing results, right? List results, nodal solution, dual solution, and y component of displacement. You can see at which node it is having maximum displacement. You can see here maximum displacement is occurring at node number 27. It is minus 11.063. It is occurring at node number 27. Okay, you can see where it is 27. It is, this is 27, I think. At this node it is having maximum displacement of minus 11.063, right? Now we'll do one thing. We'll see the animation of this one again. So before that we can do one thing. We can make the model 3D. For that we have to start from plot controls, style, and from size and shape we need to make the display of element on, right? Let us make a display of element on. Okay, this is the model. You can see in better way by oblique view. So this is the model, this is the beam, right? You can see how it will be having displacement or deformation or animation that can be viewed from here. Plot controls, animate, and you can see deform results, and we want to see deformation in the form of displacement. Okay, let us decrease the delay to see it in a better way. So by this way it will be having displacement or deformation, right? So let us close this one. Now very important things, we have applied load of 2 kilonewton and 4 kilonewton at specific locations. Suppose you want to change the load and you want to run it again. There are different options are available. One option is, first option is you need to delete the loads and you have to load again, right? Instead of doing this one, you can do something else, like you can change the code as per our requirement and see that as a second, right? Let us see that how can it be done. List, files, log files. Let us select log files. It is log file. Let us save this one. Save as log list. We are saving this on the desktop, right? Let us close it. Now we'll see the log file and we change some data. Let us see the element first. Plot element. So what we want to do is we applied a load of 2 kilonewton or 4 kilonewton at a specific location. That load we need to change it and see how the results will vary, right? So let us open this log list. You can see these are the codes. Actually we need to understand this one a little bit, right? So let us see that we initiated this one at 812, so it was started from here itself, right? Now we can see that these are the codes generated from this program. Now what we'll do is we need to change the loading, right? Let us see where we applied load. These are the boundary conditions. That means this is for actually simply supported beam. These are the code required for simply supported beam. Now let us see the force what we applied. These are the force we applied. First location we applied a load of 2 kilonewton and second location we applied a load of 4 kilonewton. Let us change these things. Instead of 2000 newton, we change this one as 10 kilonewton or 10,000 newton. And similarly the second one, instead of 4 kilonewton, we'll change this one to 80 kilonewton, right? First load we are applying 10 kilonewton and second one is 80 kilonewton. And we'll save this one, file, save, and we'll copy this one. We initiated this one from here itself, right? You can copy all these things. So this way to save your time, you need not delete all these things. Copy and that can be pasted in the program itself. Let us paste it here and let us solve it. It is showing solution is done, right? Solution is done. So we can see our results again with the different types of loads. We can see how the result will vary, right? Let us close it and see the results. You can see it from front plane. This was the object. Now want to see from results from general post processing. First of all, you see bending moment diagram. It will be from line element response. It will be number 2 and 15. Okay, see, in this case it is changed. So maximum bending moment is occurring at this location and it is 52 kilonewton meter. At this location it is having different. At this location it is actually 46.22 kilonewton meter, right? Let us see again the different things like shear force diagram. Also we can check it from here. It will be from 5 and 18. Let us see it again. It is changed at this moment. You can see maximum bending moment is occurring at this location here itself and it is 38 kilonewton and minimum it is 52 kilonewton, right? So this way, by changing the coding itself, we can get our results as per our requirement. We need not delete the load and other things. We need not delete the boundary conditions also. So any change is required, you can change it from the code itself and get the results. Okay. So this is all about our today's video. This was very simple analysis of a simply supported beam with two concentrated loads at specific locations, right? So with this one, we'll conclude our video. Thank you so much for watching this video. Thank you again. Bye. If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.